Okay. So, good morning, everybody. My name is Mohammad Al Khatib. I'm an associate professor here at Sigma Clermont Institute Pascal also. I will replace Yusuf Mizwar today. Professor Yusuf, he has a meeting, urgent meeting, and I replace him. Yusuf is the project coordinator, because we are presenting today Softmanbot, and Yusuf is the project coordinator. I am the technical manager of this Softmanbot, so I'm more comfortable with his presentation. Today I'll present to you advanced robotic technology for handling soft materials, deformable materials in manufacturing sectors, which is called the Softmanbot project. Before I start with the introduction and everything, I would like to show you a brief video. I hope the audio will be reached to everybody. Can you hear the audio?
Yes, it's working.
Yeah.
In today's industry, robots see a widespread implementation for more traditional and repeatable tasks, such as assembly and machining, while dexterous manipulation of soft and deformable material is a complex challenge that researchers are still facing today. From surgery to food handling, from packaging to manufacturing, many tasks involving the handling of deformable materials are today performed manually by skillful human operators. The intrinsic complexity of these tasks lies in the high variability of the handled material shape, making it impossible to automate their execution with traditional robotics techniques. The EU co-founded project Softmanbot started in October 2019. It develops an innovative and holistic robotic system for the handling of flexible and deformable materials within labor-intensive production processes. The developed robotic system will be composed by three main pillars: an advanced perception system to track the state of the product and collaborating with human operators, a multi-sensor adaptive control and planning platform used to regulate the product's state and which will enable human-robot collaboration and AI-based task generalization, and innovative dexterous grippers with smart mechanical design that will integrate sensors and embody grasping manipulation skills with the soft product. The Softmanbot findings will contribute to help robots play a bigger role in European factories, thereby increasing productivity and job quality. The project's consortium is composed by 11 partners from 4 European countries, coordinated by Sigma Clermont, an engineering school connected to the industrial world with a global and international perspective and strong ties to high-end research and entrepreneurship. In order to facilitate the assessment of the performance, transferability, scalability, and large-scale deployment of these solutions, the demonstrations of the project are conducted under real industrially relevant environments in 4 pilot demonstrators involving 4 key manufacturing sectors: toys, Duema, textile, Decathlon, footwear, Plastina, tires, Michelin. The Softmanbot project strives to design a modular and interoperable architecture, develop a robotic perception platform, develop a multi-sensor planning and control system, design and develop intelligent, dexterous, and low-cost grippers for deformable object handling, deliver an environmental, economical, and social evaluation. If you want to stay in touch with the latest updates of Softmanbot project, you can follow us on LinkedIn and Twitter, subscribe to our newsletter, and check the project website.
So, Softmanbot project, as you saw in the video, is by 11 partners in Europe that gather around to manipulate or propose a solution for deformable object manipulation. These partners, we submit the project in 2019, and we were granted around 8 million euros to do this project with four different industrial partners in Spain, Italy, and France. The project was began the last year of this project, and for this project, we are aiming to handle some industrial situations. And the situations nowadays can be seen that the partners in Europe now they want to bring back the manufacturing of industry to Europe. How are we going to go bring back this industry? By proposing some complex materials handling, plus we can human-centered the production with ergonomics, attractiveness, safety analysis, etc. And by this, we focus in 4 different deformable objects sectors. The first one is by Juema in Spain, where we assembly and demolding the doors components. Secondly is Decathlon in Italy, where we handle textile industry for manufacturing of texture or fabric with Decathlon. Third is with Plastiner in Spain for footwear industry, or demolding the shoe soles. And lastly, with tire industry in France with the Michelin, with assembly the tires by the superposition of components. I will go one by one just to introduce the problem of deformable objects here that we concern of. For Juema in Spain, this is an enterprise or a company located in Alicante. They work with dolls since more than 30 years, and they are one of the best in Europe in a good quality dolls. The process of manufacturing the doll, as you can see in the image and from the left to right, they pour the raw materials in the molds. They use some pillars or clamps with high force to demold these materials, as you can see in the second image. After that, they assemble these parts to form the doll, as you can see from the right images. As you can see here, the whole process is done manually. And we aim in this project is to facilitate the work of manufacturing the dolls by proposing some solutions. This solution is to help the operators to not do repetitive tasks like this, is just by supervising. Second, we call it like deformable objects, which is the textile, is from Decathlon in Italy, Milan. And here, as we can see, is the process of padding the fabrics. Padding the fabric, starting by putting the pads on top of each other, sewing around with the fabric around the pad, and stretching from the sides to not find wrinkles in it. And after that, checking again this process. Again, it's fully manually processed, and which means that the repetitive work can have a health issue for the operator. And for that, Softmanbot project proposed some solutions. For the third, we call industrial partner, we have the footwear by Plastiner. As you can see from the left image, we have the molding machine where the operator inject some raw materials in the mold. After that, using a plier or a clamp to demold the shoe sole with really high force. As you can see, he used both of his hands on the right image just to demold one shoe. And as you know, repetitive work here can finally have a health problem, some muscular injuries. And Softmanbot proposed some solution for this, for not automatize, no, it's just collaborating the robot with the human for deformable object manipulation. Lastly is Michelin, which is one of the biggest tire manufacturer in the world, one of the biggest 3 companies in the world for tire manufacturing, more than 120 years of experience. How they manufacture the tire, as you can see here, we have a drum shape process. They put the tire around this drum shape instrument, and they hold it by both hands to do sticking both parts together. And by this, after that, applying high force, as you can see here from the second image, the middle one and the right one, to apply some force on the intersection part to stick both threads together. And as you can see here, it's totally manual and needs to be helped by the robot or the cobot with the operator to do this task and to avoid repetitive task injuries. For this, why we need this Softmanbot? We need to deliver a robotic system capable of obtaining acceptable processing speed during the process. We need also to have a a solution for different objects, different sizes, different forms, no fixed position. Also, we need to have a robot and a hand that is dexterous, has a property of dexterity that needs to perform the task. We also need a high variability in the parts quality, color, hardness, and we also aiming most of the time to worker health problems due to repetitive tasks. For this, we are 11 partners in Europe. We propose a solution to have a common software platform based on ROS, robotic operating system, that having common grippers technologies with sensor integration unit, tactile, and other sensors such as cameras. And we have a common integrator that guarantee the coherence of this project. And we started this one. If you have more detail about the partners, you can go to our website, softmanbot.eu. So what we propose is to have 4 different robotic cells, one for each industrial partners, one for the tire sector, one for the toy sectors, one for the fabric, and the last one for the shoe. As you can see from the top left, we have for the toy sector, we have a robotic cell that can take the toy, demold it, and after that do the assembly. We have from the top right, we have the robotic cell for the fabrics. When we took the pad, we have a specific gripper for that. And then another robot is not mentioned, is not shown here for doing the stitching. From bottom left, we have the robotic cell for the shoe sole, where the operator and the robot was together to demold and evaluate the quality of the shoe. And lastly, we have from bottom left, right, which is the for tire use case. We have the 2 robots that can receive the tire thread, and perform the task to put both of them into each other and do fixation of these 2 threads together. What we have challenges, as you mentioned, for this workshop is the deformable objects of manipulation. For that, we have different challenges based on deformable objects. First, we need to know how to handle these objects. For that, we have different kinds of objects, from toys to texture to tires. For that, we need to have a smart, dexterous grippers. These grippers should be adaptable for the use cases, plus should have some specific properties, which we will discuss after. The second challenge is to learn how to do the task. Like this, we need to do a human-robot collaboration. And once we mention the human, we need to also assure the safety and the ergonomy of the human. Third is to identify the objects, locate them, and to find the best resting positions, which we are working with deformable objects. We need to locate them with robotic perception based in multimodal, such as tactile, such as also vision systems. And lastly, we need to control the pieces deformation while manipulating them, which we need also multi-sensor control and planning. As you can see here from the image, we have the main 3 pillars. We can call it as a pillar of this project, which is the robotic perception, smart dexterous grippers, and multi-sensor control and planning, which we will take each one now. For the first one, which we have a smart dexterous gripper. As you can see here from this figure, we have proposed 4 different grippers. Each gripper has different properties based on the deformable objects. From the left, we have the gripper for the tire use case, where we need a multi-finger gripper that can, from one side hold the first thread, from the second side hold the second one, and put them on top of each other. So we need to have a long stroke plus multi-finger gripper. For the second one, we have a gripper that has properties of high forces. This one, we use it for 2 use cases, for the toys and the shoes, for demolding. This gripper can reach more than 150 newtons for removing or demolding the objects. And also, it has the properties of tactile, which means that we need to get a feedback from the object once we receive it, because once you put the gripper inside the mold, the vision system cannot be adaptable there. For that, tactile properties is important. For the third one, we have the long stroke gripper, which we propose for assembly of the toys, different parts of toys from the head to legs, arms, which means, and the body, which means we need to have a gripper that's very in the stroke of the gripper, which means that can open very wide or can short and very narrow. And lastly, we need a gripper that have special task. This gripper needs to remove the wrinkle of the fabrics, and after that, do the stitching of the pads on the fabrics. We have some first results, as you know, that the Softmanbot project is still going, and we have first preliminary result from the top two, which is the gripper for the demolding. As you can see, it's about the long stroke of the gripper, can be more than 40 centimeters, which can adapt for different kind of dolls, of different kind of toys. From the middle left, I have a video to show you where we have a gripper for the tire. You can see it's long stroke, and after that, multi-finger gripper. From the middle right, we have the assembly gripper for the toys, where it's very precise. That means can open in very short centimeters or millimeters, the precision, and it's good for simply adding some force to simply the toys. And lastly, we have the gripper for demolding. For demolding, it should have a really high force that can replace the human process. And we put a force sensor, and you can see here in the meter that can reach more than 150 or 160 Newton, which really, really high force to repeat the task. This is for the grippers. For the second thing, the challenge is the human-robot collaboration, and we know why we need learning the human process. For that, it's not always need to manipulate the object to reach a final position. It's also we need to know how to manipulate it. Doesn't mean that the final position is the important one. Also, how to do it is really important. And by this, we work on learning from demonstration, such as screw-based DMPs, dynamic motion primitives, bilateral liberation, and also because we mentioned that there is a human in the process loop, we also add some human safety and ergonomics. For the human safety, we established some areas that there is nothing happen to the robot, work normally. Some area in orange that the robot needs to reduce velocities. That means we need to have a function that reduce the kinematics of the robot. And some red areas, which means that the human within the workspace of the robot, which means that the robot should stop moving, because when you work with high forces, especially for demolding, more than 150 newtons, we need to empty the space, the workspace of the robot. We need just to have more safety for the human. Second thing, because we are working with a human that can evaluate the process, that can help the robot to do the task, and after that the robot repeat it. For that, we need to know the ergonomics, such as fatigue, some health issues, the posture. Also, we need to evaluate the worker ergonomics to have it checked up in every hour. I can show you some work on learning from demonstration. We can see here some using DMPs. From the left, we can see that the operator do the task. As you can, we have some QR codes. We have we save the trajectory by the operator, and after that, in the right video, we have the robot repeat the task the same as the human did. And as you can see that the robot follow the same exact trajectory as the operator. As we said before, that not just the last phase of the process, which is the last position of the object, is important. Also, the way to do the manipulation is also important. We also have some videos about using some learning techniques to learning from demonstration to demold the shoe. As you can see, the operator do the task using some plier with some QR code to calibrate it and also save the trajectory. And after that, the operator, as you can see, they choose the best grasping position, and then the robot perform the same task exactly with the same maneuver. Lastly, we can not just teach the robot by saving trajectory. We also can do some teleoperation, bilateral teleoperation, that we show the robot how to do the task. And after that, the robot can do the task one more time by learning from demonstration. And by this, we can save time, we can use work from distance, etc. And as you can see here, we have a deformable object, which is a bottle, and the operator teach the robot how to handle these objects. For the third part, or the second pillar, is the perception. As I mentioned, we work with 5 different types of deformable objects, such as dolls, shoes, tire treads, and also fabrics. For this, we face some problems or challenges, such as object segmentation, shape detection and tracking, wrinkle detection, and also contact point detection. And also, we know that the human in the control loop. That's why we need to know where is the human exactly in each second, which means we need human 3D pose estimation. For that, we propose in this consortium, we propose we call it some solutions for each part. For the visual perception, we talk about particle SFTs and also position-based dynamics, as rigid as possible models. Also lattice, which is the next advance from as rigid as possible, which is lattice as rigid as possible model. And also now they are working about graphical neural network. These models can give you the shape of the objects. And also some of them can give you also segmentation of the objects that can be used for the next step, which is modeling and controlling the manipulation of deformable objects. Also, we also work on contact determination by work on contact determination based on Courseret model. Also, contact determination based on probabilistic ensembles. Also, we use some tactile perceptions for grasp stability, which means that we add some tactile sensors on the gripper hand and evaluate the grasp stability. These sensors is like papillary array tactile sensor, digit tactile sensor, thick scan tactile sensor, and sync tactile force sensor. Finally, once we know also the human is around, we need to know where is the human using open pose, 3D position estimation, and also we know the recognition of some actions by the human. That means like he's standing up, he's doing the manipulation, he's away from the machine, he's retreating back, or doing some activity. And we use some deep learning methods to recognize these actions. Some of them result that can we show that for the tire thread, as you can see here, is using as rigid as possible to deformable objects driven shape deformation. And as you can see, it can detect it really nice, track the deformation in each frame. Also, we have this is for the shoe sole. This is using the lattice one. As you can see, it's like around the box, around the objects, and detect the nodes using the lattice as rigid as possible. For this one, we finally work on how to manipulate and how to control and plan the deformable objects manipulation. For this, we propose some shape serving techniques from finite element methods to meshless shape matching. Also we use as rigid as possible geometrical deformation model. Also, we need to know how to grasp the model and how to know if it's grasping it's stable or not. For this, we propose some methods on dynamic grasp synthesis, grasp affordance, deep Q-learning, and grasp stability. For motion planning, also we use the same model as ARAB, as rigid as possible, geometric information model. We use also G-Explore, which is a model based on G-Explore algorithm. And also we work on optimal control for motion planning. In the end, we propose in this project is to generalize all methods in one. That means that I can use one model for these 4 use cases or for these 4 objects. We use that multitask reinforcement learning and meta reinforcement learning. For some results, on the left, I will show you some results about how we manipulating using some ARAB for, as you can see, once we change the sheet in the image, the robot needs to follow the deformation of the object. On the right, we have the optimal control, but we have different scenarios, different starting position, and we need to know how to reach the final position by sticking 2 threads on top of each other. Finally, I want to show you this video about as a possible shape servoing. Where we define the final pose of the object, of the deformable object, and the 2 robots manipulate the object to that shape. We use different kind of materials, from papers to the shoes from Plastiner company, and also tires from Michelin company. This is when we use the a tire thread with different kind of shapes, final shapes, and both of them the robot succeed to reach that shape. In conclusion, I present to you Softmanbot project, which is advanced robotic system for handling soft materials, deformable materials for industrial sectors. We are around 11 partners that from 4 different countries in Europe that work on this project. I propose to you the 3 main pillars of this project, which is the robotic perceptions, the smart dexterous clippers, and the multi-sensor control and planning. We propose to you the 4 different industrial sectors that we will work on, 4 different deformable objects, from toys to footwear, textile, and tires. Finally, if you have any more questions, you want more details on one of the methods or one of the how to do the planning or suggestions, feel free to contact us directly using the softmanbot.eu site, or you can go directly and contact us directly. Thank you.
Thanks a lot for the presentation. So now it's time for the questions. So are there any questions from the audience? So you can use, again, the Slido or the Zoom, or just raise your hand. Are there any questions in the room, Daniel?
I don't think so, although it might. Oh, we do have one question. You might have to come up here in the microphone. Yeah. We're going to get the microphone checked during the break, but it won't be for another hour or so.
Okay. Should I talk here or here?
Into the laptop.
Okay. Hi. Thank you for your great presentation. For the last video that you showed us, how did you identify your deformable object using your mesh data? The point cloud. Yeah.
For this one, we have 2 options. We worked before in the beginning of the project on textures, and based on the texture, I would know the deformable object's status now, and then I can move it, or using the Arab model to move it to the last position or the final position. Nowadays, we are working on different techniques, not using the texture. It's called textureless technique, using deep learning methods. In the video, it's based on texture.
Okay, thank you.
Because of time, I think we should move on to the next session.
No, but we have a last question. Let's go through the question. So there is a question on Slido that is, do you use any simulators in your work? If so, which ones?
For this moment, we don't use any simulator. We work directly with the robot.
Okay.
We have some partners planning to use some reinforcement learning techniques. But for this moment, as I told you, the project is ongoing, and I think they are going to use some real to sim to real, which is under process now.
Okay, last question that is here in the chat. So it's Jiangzu and says, thanks a lot for the presentation. It seems in the product you have specialized the solution for each scenario. What do you think are the most critical challenges that you cannot have a generalized solution?
Thank you for the question. I think we have some use cases have little bit different issues than the others. For example, we have for Decathlon use case, which is about the fabrics. We need to stretch the fabric using a specified paper and then do the stitching. And by this is different than other methods. For this, the generalization, the ideas or the solution will be a little bit difficult.
Okay, yeah, that makes sense. I guess it's really critical to have a really general solution for everything.